And we're back. So in the last video, to recall, we were computing doing the horrible computation of the Fourier transform of chi-q squared. Obviously, doing that computation for higher powers of chi-q is a nightmare, but fortunately there is a way to do it all in one fell swoop. And so clearly, as r increases, we're going to be an exponential amount of labor that is going to an exponential increase in the amount of labor required to manually do things. So the alternative that we're going to do comes from let's go back to this recursion relation we found between the Fourier transform of the nth truncation of fr, where fr, recall, is this just ignore the exponent here. It's this f series as n goes to infinity. That's a raised to the power of r. That's what fr is. So yeah. So this as n goes to infinity would be f2. If we made this a 3 and made n go to infinity, this would be at the integral of f3, and so on. So the idea here is that if the natural thing to do is that since fr's nth truncation converges to fr, it would seem that we would just assume that, well, if this limit exists, and indeed if we can define mu k hat of t as the limit as n approaches infinity of this thing, and if it exists in some sense, that is with respect to a certain topology for all the k, we would then have the following functional equation. And so, ideally, we would then want to show that the measure whose Fourier Stieltjes transform satisfies this functional equation is in fact the same thing as fr. However, proving this convergence is subtle. So instead, what we're going to do is we're going to show that if these exist, then they induce a measure which acts on functions in a certain way, and any measure which acts in that same way, given any measure which acts that same way, its Fourier Stieltjes transform must satisfy this functional equation. There is one additional issue, however, that's going to complicate this. So far, if we're just thinking of this in terms of measures, quasi-integrability is more than just being able to say that fr, by some weird formula, induces a measure. Quasi-integrability instead is not only does fr induce a measure, but if we sum the Fourier series generated by the Fourier Stieltjes transform of said measure, the result of this Fourier series, it actually converges to fr as a function. But to begin with, we're going to need the following useful identity. So it gets into particular that if we have f hat and g hat are functions on zp hat, and here all you need for f hat and g hat to be taking values in a single commutative ring r. So then we have that the sum over all t of f hat t times g hat of pr times t is equal to the same thing as this sum. It's where we take sum over all t, but then we have f hat of t over p to the r plus the sum of all over all s less than or equal to p to the r. And so in this case, this particular map here, for those of you who are more fluent with functional analysis, this defines a duality pairing, a duality bracket between the C0 of Z2 hat CQ and B of Z2 hat CQ. This is the space of all functions from Z2 hat to CQ that decay Q-adically to 0 as T's 2-adic absolute value goes to infinity, whereas this is the space of all bounded functions from Q-adically bounded from Z2 hat to CQ. And in particular, this pairing is then a CQ is a continuous CQ bilinear form from this cross that to the field of scalars CQ. In particular, if we define the operator LR on the C0 space, which takes any function g hat and precomposes it by the multiply by p to the r function, we then have that this formula is we're computing the adjoint of LR, denoted LR star, with respect to this duality pairing. And then in particular, this duality it behaves like an inner product. In fact, it is an inner product on C0 because this is always going to be conversion when both f hat and g hat are in C0. So the proof of this guy is by induction on the r equals 1 case, and just in my own notes and just by hand, I will refer to this as the adjoint identity. So we start by induction on r equals 1, and then the argument comes from the observation that if we want to sum f hat over all t in zp hat, well, let's write them all out. This is f hat of 0, and then for the non-zero elements, every non-zero element of zp hat is going to be a rational number, strictly between 0 and 1, whose denominator is a power of p, and whose numerator is co-prime to p. And so in particular, though we get that by writing, this is using what I refer to as the numerator enumeration in the first part of episode 8. This is going to be equal to the sum from n equals 1 to infinity, and then the sum from k equals 1 to p minus 1, and the sum of L equals 0 to p to the n minus 1 minus 1. And this is then going to give us all the possible t's. So for this, now let's just multiply everything out. So here's f hat of t times g hat of pt. Pull out the 0 term. And what we get using this identity is this. Here we reduce the denominator. We increase n by 1. So then we pull out a 1 over p there. And then we pull out the n equals 0 term. And when we do this, what we'll then do is we're going to sum L. We're going to break this up as the sum from L equals h p to the n minus 1 and h to h plus 1 p to the n minus 1 minus 1. The reason why we're doing this is because here, actually no, this is just we're doing this. And so with this particular breakup, we then add, no, I remember now. The reason why we're doing this is because this function right here, g hat, if we increase L by p to the n minus 1, that's going to be the same thing as increasing this numerator by p to the n. And since g hat is periodic mod 1, that's going to then leave g hat unchanged. So we're splitting the L sum here into the sums of the level sets over which g hat is constant. And then so we do all of that, and we do the re-indexing. Blah, 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 blah. Just look at all of this. I personally very much enjoy this sort of accounting business. And so we're doing everything here. We've now put all this together. So then we want periodicity, and then we can, by summing over K, PL, and N, K, PL, and N, K, L, and N, that all those three terms combine to be a sum over all T. And then here we just re-index h as k, and then we have k equals 0 to p minus 1 everywhere, so we pull that out, and this is, of course, this is the t equals 0 term, but these two cancel out, and we're done. And so this proves the r equals 1 case, and then for the general case, we just show that the the rth case, we apply the r equals 1 case to this, and then we re-index, and we get what we want. So now we need to deal, so in our first step, we're going to show that this limiting process makes sense in a certain sense. And for this, we're going to need some functional analysis. No, actually, before that, we're going to do something else. Yes. So we do the key work of showing how the pointwise limit of this induces a measure. In other words, I'm going to say that before rather than talk about this convergence, suppose that this holds true for some measure's Fourier transform. Then that measure must affect functions in a certain way. In particular, let's define f0 hat of t to be the indicator function of 0, and suppose that for each k each positive integer k, there is a function fk hat from z2 hat to cq, which is q-adically bounded, so that for every r, the following functional equations are satisfied. Letting this guy denote this measure. So this thing so far has no relation to the F series. of fk. It's just the way notation we're using. So for letting this guy denote the measure that possesses fk hat as its Fourier Stieltjes transform, we then have that for every continuous, here k can be CQ or any metrically complete extension of the the field of q-adic rational numbers. Then for any continuous 2q-adic function g, the integral of g f dz is going to be given by this formula. Conversely, suppose we have a family of measures d mu k such that this identity holds true for all continuous g and for all r in n0. Then it must be that mu hat 0 of t is a constant multiple of the indicator function 0, and that the mu hats satisfy our recursion relation. So, in other words, if you have a measure that whose transform looks like this, then it must affect functions in this way. And if a measure affects functions in this way, it must have this as its Fourier transform. Note that, first of all, the functional equations make sense when, that is this one, when r equals 0. There we get the following. Since f0 hat of t was defined to be 1, 0 of t, when t equals 0, this becomes 1 equals 1 plus 1 over 2 times 1, and we get the right thing. On the other hand, if t equals 1/2, this is 0, 1 minus 1 over 2, and then this is going to be 1 because 1/2 times 2 is 1, which is 0 mod 1. However, if t has a denominator greater than or equal to 4, both f0 hat of t and f0 hat of 2t vanish. So both sides of this equation vanish when t is bigger than that. So everything works when r equals 0. On the other hand, if we have any measure mu hat 0, d mu 0, whose Fourier Stieltjes transform mu hat 0 satisfies this formula, when t equals 0, everything works. When t equals 1/2, we get that this side is 0, and so that forces mu hat 0 to 1/2 to be 0. And then by induction, we have that mu hat of 0 of t equals 0 for all t with a 2-adic absolute value greater than or equal to, this should be a 2, not a 1/2. And so this then means that mu 0 hat vanishes everywhere except at t equals 0, which means that mu 0 hat of t is a constant multiple of the indicator function of 0. So now let's move to r is greater than or equal to 1. Suppose that the fk hats of t exist and that they satisfy the relation, the recursion relation. Then letting g be continuous, by definition, the integral of this thing, because we know that this is the Fourier transform of fr, this is our Parseval-Plancherel formula. We then use our recursion relation for fr hat. Note the negatives here. And then we pull out k equals 0. And now we're going to use the adjoint identity on this function and this function. So the 2 gets passed from a numerator to the denominator here, and we sum over all the t's in between. So this is going to be the sum from j equals 0 to 1 plus j over 2. Then we just rearrange, and here we are just using the definition of the integral with respect to g of t. So note here that this is sum over all t of some function of t times fk hat of negative t. So that's by definition is the integral of the sum of the Fourier series here times fk of z. This is going to be guaranteed to converge because g is continuous, and therefore g hat tends to 0 q-adically. And here, when now we do a change of variables. Do we do a change of variables? No, it's that. This just ignore. This line is bad. It doesn't belong there. This gives us everything we need. And no, I'm being stupid. No, we don't ignore it. We then use the adjoint again. So here, now that we've pulled the 2 out, we're now going to take the 1 over 2's and we're going to use that to put t to there. And then so this gives us here, and since g hat this is the Fourier series, we then sum this up and we get that this is 1 over 2 to the k g of 2z plus q over 2 to the k g of 2z plus 1, which is what we want. And then to show the other direction, we just reverse all of these computations, and then it shows that any functions, any measures satisfying these integral identities, then necessarily their Fourier Stieltjes transforms satisfy the recursion relation. And in particular, we can just do this specifically with the case where g is e to the negative 2 pi I tz. So now a trick. Treating fkz dz, again, it's purely a formal symbol. At this point, it has nothing to do with the f series that we call fk of z. Let's pull the k equals rth term out of this side of the functional, out this side of the formula. So here we then get this thing plus this thing. Moving everything over, we have the following equation where LR is this linear operator on the space of continuous functions. It sends g to g of z minus 1 over 2 to the r plus 1, g of 2z minus qr over 2 to the r plus 1, g of 2z plus 1. And notice here we're summing, this is now truly recursive because it allows us, it tells us that we can compute LRG integral against FR dz. We just need to know these integrals for fk dz for all k strictly less than r. Now first, let's just do some routine work. Let r be a non-negative, be a positive integer, and let L be any prime of z, including the infinite prime, and let k be any metrically complete extension of QL. So that means if L is the infinite prime, QL is just r. Then LR is a continuous linear operator on the space of continuous functions from z2 to k. Let everything be as given, and then this is the definition of LR of g. This is going to be continuous whenever g is continuous, and since LR is obviously linear, this then gives us our linear operator. To show that LR is in fact a continuous linear operator, we need to consider its operator norm. Its operator norm in this context is the supremum of this thing here. So this quantity, what we're going to do is we're going to take the supremum of the L-adic absolute value that LR of g of z attains over as z varies among the two adics. And then we're going to take the supremum of that quantity over all continuous functions from z2 to k whose norm is less than or equal to 1. Note that this formula holds independently of what L is. And here now we're just going to use the fact that the 2L adic norm is a norm. It has the norm properties that's equal to this. So by the triangle inequality, we could apply the ultrametric inequality if L was a finite prime, but I just want to cover all the cases at once, and so we get all of this. And here we just pull out the constants, and so this then gets us the constant CRL, and then we have the continuity, because we can just take the supremum, and we get that the operator norm of LR is bounded by CRL. Therefore, so it's LR is a bounded linear operator, and therefore it's continuous. So then with all this together, we then have that for r greater than or equal to 2, and for continuous g, letting our measures be as described in previous proposition, we then have that the integral of LR of g against the FR dz is given by this formula. So what this then tells us is that if I know how to integrate functions with respect to fk dz, then I can use that to integrate functions with respect to fr dz. In particular, suppose I wanted to integrate some continuous function g against fr dz. Then, if we could find a continuous function little g, such that LR sends little g to big G, we could then use this to compute this integral as follows. The integral of g fr dz is all of this, and here we're going to use the inverse of LR. This shouldn't be a 2, it should be an r. So as an example, setting r equals 2, we get that the integral of g f2 dz is equal to the integral of L2 inverse of big G dz plus this integral, blah, blah, blah. Since f1, of course, in this case, is just xq2, which we already know how to integrate with respect to which, since we already know how to integrate against f1 z dz, we can then use this to define what it means to integrate against f2. And so all we need to do here is show that LR is invertible for all r greater than or equal to 2, and then we can construct FR of z dz recursively. In other words, we know that f0 is just the constant function 1, so it has a Fourier transform and everything. Then we make the decision to define f1 of z dz as the measure which we get when we use the Fourier transform of f1 of z, which we know is quasi-integrable. Then what we're going to do is show that once those two initial conditions are set, this recursive formula will then give us a formula for fr dz, and that formula will have the correct Fourier-Stieltjes transform. Once that's done, all we'll need to show is that that particular Fourier-Stieltjes transform generates a Fourier series which sums to fr, and then we'll be done. So now comes the functional analysis I was talking about. So just to be clear, because we're dealing with the inversion of a linear operator on an infinite dimensional Banach space, let's just recall a bit of the basics. In particular, the uniform boundedness principle, but in this case, potentially in a non-Archimedean Banach space. Fortunately, the quality of a Banach space has no bearing on whether or not the UBP holds. As Shikov explains in his Banach space paper, the references in the description, because the fundamental results of functional analysis depend on the all-important Baire category theorem, the uniform boundedness principle, the closed graph theorem, and the open mapping theorem will apply in any Banach space, whether it's an Archimedean or non-Archimedean. Surprisingly, the Hahn-Banach theorem is a bit more problematic in the non-Archimedean case, and Shikov's paper or my dissertation give a more detailed discussion of that for those who are interested. So let's just review. The uniform boundedness principle says that let E and F be metrically complete valued fields, let X be a Banach space over E, and let Y be a normed vector space over F. Let L be any set of continuous linear operators from X to Y. If for every X in X, the L's are uniformly bounded, so in other words, if the L's are uniformly bounded in norm pointwise, then the L's are in fact uniformly bounded normwise, whereas usual, the operator norm of L is the supremum of the Y norm of L of X taken over all X in big X, with big X norm less than or equal to 1. From this, we then get the following crucial corollary. Let E and F be metrically complete valued fields, let X be a Banach space over E, and let Y be a normed vector space over F. If we have a sequence, Ln, of continuous linear operators from X to Y, such that the pointwise limit exists for every X, then the map which sends X to the pointwise limit is a continuous linear operator from X to Y. For both the uniform boundedness principle and this corollary, the classic proofs, such as the ones available on Wikipedia's article about the uniform boundedness principle, they work independent of whether E and F are Archimedean or non-Archimedean. Now, before we cover the issue of inverting L, R, we need to deal with the following simple computation. The basic idea, indeed, is we know that the space of continuous functions from Z2 to our field K, they have the indicator functions form a basis for them. So in order to invert L, it suffices to invert L on every indicator function. In particular, let R be a non-negative integer, let n be a non-negative integer, and let k be between 0 and 2 to the n minus 1. Then for all m between 0 and n, the mth iterate of 1 minus LR sends the function z, the indicator function for the set of z congruent to k mod 2 to the n, to the indicator function of the set of all z congruent to the mth shift of k mod 2 to the n minus m, and then we have a multiplicative factor here, q to the r to the number of ones in k mod 2 to the m, divided by 2 to the m times r plus 1. And again, theta 2 here is the 2-adic shift map, which it's z minus the value of z mod 2 all over 2. So if z is congruent to, if z is even, the shift map divides z by 2, and if z is odd, the shift map subtracts 1 and then divides by 2. So now, by definition of LR, we have that 1 minus LR, it's equal to, just go back to the definition, which is this guy. We have that 1 minus LR is equal to this thing. And they're just by everything by definition. Now we use, again, this just justifies why I believe Iverson brackets are the greatest notation I've ever seen. So we're going to divide by 2, and then that has the effect of decreasing this exponent by 1. And so here, if k is even, we can do this, but if k is odd, this is going to automatically evaluate to 0. So this then gets us k is even, and z is congruent to k over 2 mod 2 to the n minus 1. Likewise, for 2z plus 1 congruent to k mod 2 to the n, we get that the k has to be odd, in which case this is the same thing as z is congruent to that. So we have all of this. Now we use the shift map. If k is even, this is k over 2. And if k is odd, this is k minus 1 over 2. Thus, regardless of the value of the parity of k, what's in here is what we get by applying the shift map to k. And then, in particular, we can write this as the following. We then pull out this guy. And then here, this is the same, we can write this, that this is going to be qr to the number of ones in k mod 2. So, therefore we've shown the following. By an inductive argument, then shows this. Just by multiplying everything out. And now we're going to use the fact that since k is a non-negative integer, it can be uniquely written in Hensel series form here, where lambda 2 of k is the number of 2-adic digits of k. Now we make an observation. If I take this number and I apply the shift operator j times, and then project mod 2, that's a way of extracting the coefficient Cj. So for example, if we just do this mod 2, we get C0. But if we apply the shift operator once, the smallest term of this would be C1, and then all of the others would die mod 2, so this would be C1, and so on. And so in particular, we then have that applying the shift to k j times, and then projecting mod 2 is the same thing as Cj. And Cj is either going to be 0 or 1. And here, note that if we sum from j equals 0 to m minus 1, that's just saying we're going to be counting the total number of ones digits in k up to the coefficient of 2 to the m minus 1, which is of course the same thing as the number of ones in k mod 2 to the m. And that finishes the proof. Now, this argument I really enjoy because it's very silly. Let R be be an integer greater than or equal to 2. And for this sake, let's let Q be, again, it's our odd prime. And suppose that this inequality holds. Then, for any metrically complete field extension f of Q, and actually this should be a metric as a valued field. LR is an automorphism of the Banach space of continuous functions from the 2-adic integers to f. In particular, for any non-negative integer n and for any k from 0 to 2 to the n minus 1, LR inverse sends the indicator function of k congruent of z congruent to k mod 2 to the n to this guy. And because of this, since every continuous function in G, every continuous function big G in this space is uniquely represented by a Vanderput series, and since the inverse of since if LR is an automorphism, its inverse is also going to be an automorphism, therefore going to be continuous, we can then use Vanderput series to compute LR inverse of G term by term. So again, the argument is simple but slightly insane. So, since LR is a linear operator, formally, we can write the following identity, where here 1 denotes the identity map on this space. As is classic in functional analysis, if we can show that this geometric series converges an operator norm, that will then tell us that LR is indeed invertible in our Banach space, and that LR inverse is also an element of the Banach space. So, because the indicator functions here span our space of continuous functions via Vanderput series, to compute LR inverse, it suffices to figure out what this is for all m, and then see what happens when we sum the geometric series. Well, thankfully, we've already done this. The first thing that we note is that by this formula, 1 minus LR of the constant function 1 is going to be equal to q to the r plus 1 over 2 to the r plus 1. And because of this, by linearity, 1 minus LR to the n plus m, we can factor out the applying it m times. Here we applied n times. And here, this is the fun part. When by the proposition that we just showed, this goes from being n minus n. And then, so this will then automatically be equal to 1 for all z, and so this is just a constant, and therefore we get that this is the same thing as applying L minus LR to the m to this constant function, which it factors out, and then, of course, we apply this m times and use this formula to then conclude that this is what happens here. So what this says then is that if we apply 1 minus LR m more times than this, the exponent of the modulus here, that's the same thing as multiplying by this factor. So, and now this is actually very significant because this is it turns out this is our untangling method. It's the exact same idea, except we're now, before we were looking at the untangling from the Fourier transform side, but here we're looking at looking at it from the F series side. So let's consider this partial sum. Then, if we pick big M to be large, in particular larger than little n, and here little n is fixed, we get this. So this is everything when m is less than little n. And then here, by reindexing, this is when m is greater than, the exponent is greater than little n. And here we then use, this is the formula for this, as we just proved, and then this is here. This, of course, is a geometric series in M, and we get this thing. So, here's where the fun part comes in, or insane, depending on your definition of fun. Since q to the r plus 1 over 2 to the r plus 1 is not equal to 1, it's a rational number not equal to 1, and technically I should say that this is not equal to negative 1, but that's irrelevant here because q is positive. Because this is a positive rational number that is not 1, and whose numerator is not 1, there exists a prime L of z, possibly the infinite prime, so that this rational number is an L-adic integer. If we fix such an L, let K be any metrically complete extension of QL. For brevity, let's set S big M to denote this thing, and then let S denote this thing. And then our formula for this partial sum here is then the same thing as Sm, this guy, minus S, this guy, is, minus this guy, also minus the constant term there, is equal to the divergent term of this. Now here's where, as I said, here's where the fun part is. This here n is, again, n is fixed. So as big M goes to infinity, this quantity behaves like this quantity to the m. Since we've picked L to be a rational number, to be a prime, for which this number has an L-adic absolute value strictly less than 1, this Sm minus S is going to converge to 0 L-adically as m goes to infinity. And in particular, we're taking supremum norm. And so what this then says is that, by definition of the limit, this limit exists and converges L-adically. So in other words, by picking our field extension K, in which this quantity has an L-adic absolute value less than 1, we then get the invertibility. So we've chosen the field extension where LR is invertible as a linear map of the Banach algebra. And so what this then shows is that LR inverse exists in this Banach algebra, and this is how it's done term by term. And because LR is continuous, LR inverse is therefore going to be continuous, and therefore we can use Vanderput series to compute LR inverse of f for every continuous function from f from z2 to k. So this makes LR into a continuous linear operator, and therefore in particular an automorphism of C of z2k. And indeed, when just verifying everything, its left inverse and the right inverse are equal to everything. And so both LR and LR inverse are automorphisms of this Banach space. Now, we're getting a little bit even sillier. Let's forget about the topological structure of this Banach space for a moment. Then LR and LR inverse are automorphisms of this vector space. Now let's dig down into subspaces. Specifically, so we started with K, which is a metric completion of QL. Well, we can then go from QL to Q, and then instead of considering here, we'll equip CQ with the discrete topology, in which case what we have here is that this is just the two Adic Schwarz-Bruhat functions with Q coefficients in the rationals. In other words, we're going to be restricting from the vector space of continuous functions from Z2 to K to the vector space of locally constant rational functions on Z2. Now, so a glance at this particular formula here, this is, everything here is finite. This is a rational number. These are all rational numbers. So what this says then is that LR inverse sends this function, this rational valued indicator function, to a sum of rational valued locally constant functions. And so in particular, by this formula, we then have that LR inverse is defined on the space of locally constant functions taking values in Q. So that means the restrictions of LR and LR inverse, we go from this space to this space, and we have an automorphism. And then the fun part, the even more fun part. So we've showed that LR can be inverted when we're working over this finite linear combinations of indicator functions. Since LR is continuous in every metric completion, in a C of Z2F for every metric completion of F, we then allow our tensor with F to extend our scalars from rational scalars to scalars in F, and then by the continuity of LR and LR inverse, we then get the invertibility of LR on C of Z2F simply by using the Vanderput series term by term, to compute it term by term. So yes, that's the argument. It's very fun, and again, it's inherently frame theoretic. But we're ignoring the tradition that one sticks in a Banach space over a single field, and instead we're just picking the fields willy-nilly in order to get what we need. And so again, this whole argument is strongly reminiscent of the untangling analysis, and I find it this whole thing deeply suspicious, and we'll get more into that in a bit. And what this would then suggest is what we want to study are no, I'll just get to it later. So now our big existent theorem is going to come in quite a few parts, some of which are rather involved. So let Q be an odd prime, and let's let again FR is just this F series. Then FR induces a 2Q adic measure, denoted FR dz, in the sense that FR dz is a distributional solution of FR's functional equations, by which I mean that these integral formula hold true for all continuous g. Again, note that this does not show that FR is quasi-integrable, because it says nothing about the convergence of the Fourier-Stieltjes transform of this measure, the convergence of the Fourier series generated by this transform to FR itself. We proceed in 2 steps. First, we construct the measure we call FR of z dz, and then we show that it solves the functional equations in the desired way. The construction is done by induction on R. As we saw in episode 1, this is the relation between chi q and x q2, and then so this is basically a repeat of the argument that we gave earlier about the mu hats and the f's. And so here, we then use our L2 operator. So since L2 is invertible over this thing, we can then define a measure f2 of z dz by this inversion, and then it will and then by this definition, this distributional equation holds true, and we then consider by induction, and we get what we want. So now, this is now the hardest part, is that we need to show quasi-integrability. So we haven't just found a distributional solution of FR's functional equations. Rather, this distributional solution, its Fourier transform, generates the Fourier series of FR. And unfortunately, this is the hard part, so it's not possible to do this without dealing with some degree of horribleness. Fortunately, I think it's significantly less horrible than the explicit case, but thankfully we can at least motivate the horribleness. So as we saw in our previous theorem, we can, because LR is invertible, we can define this measure recursively by this following formula. Now we're going to exploit a trick. Recall that the summing the Fourier series here, we call this resummation, and it's the same thing as convolving the measure with the nth Dirichlet kernel. So what we're going to do is we're going to consider this formula when G is the nth Dirichlet kernel. Then, as n goes to infinity, this part is going to converge to, it's going to be this Fourier series, and so all we need to do is then show that this side converges to this thing, ignoring the dz, or this thing, depending on the value, ignoring the dz, and then that will then give us the desired result. Yes. So this in particular will be using, this is where the functional equation characterization of FR comes true, as well as the rising continuity, which will then give us the desired limit. So in particular, when we plug in the Dirichlet kernel for G, we get this integral. So all we need to do then is to compute the right-hand side here as n goes to infinity, and we need to show that it converges. In practice, this can be done by hand for FR by manually computing the integrals on the right by induction, and then showing everything converges, but this argument takes up a great deal of space. As such, we will deal with it in a single general lemma. And the idea is that we're going to be studying integrals of the following form, where chi is quasi-integrable with respect to the simple 2Q adic frame. Here, j is in 0, 1, and z is in 2 adic integers. The argument will show that provided chi satisfies certain asymptotics, in particular the resummation, provided the resummation of chi satisfies certain asymptotics, the limit of the integral as n approaches infinity will converge to a certain closed form expression that is nice. First, however, we're going to need a lemma which will significantly simplify some of the computations to come. And this lemma is right here. So let z be a two-adic integer, and let n and k be non-negative integers. Then we have that the number of ones in the nth shift of z mod 2 to the k is the same thing as the number of ones in z mod 2 to the k plus n minus the number of ones in z mod 2 to the n. We proceed by induction on n. Here's the Hensel series of z, and here's the Hensel series of the shift of z. So projecting, we get the following. So the digits of shift mod 2 to the k are d1 through dk, while the digits of z mod 2 to the k plus 1 are d0 through dk. So, counting the digits, we get this, which proves the base case. Now for the inductive step. Suppose the kth case holds true. Sorry, the nth case holds true. Then the n plus 1th case is this, which is what we want, and that proves the identity. So, in order to make things less horrible, here's some useful notation. Let k be a set, let x be a field, and let f be a k-frame on x. Let fn and gn be sequences of f-compatible functions. I then write fn of x is f equal to big O of gn of x as n approaches infinity, to mean that for each x, there is a positive real constant ck and an integer nx greater than or equal to 0, such that the semi-norm, the frame associates to the point x of fn, is less than or equal to cx times the semi-norm that fx that applied to gn. In other words, like for the simple 2q-adic frame, this would mean that the q-adic absolute value of fn at a z with infinitely many digits is less than or equal to the q-adic absolute value of gn at that same z times the constant, where the constant is allowed to depend on z. And on the other hand, we change things to using the real absolute value if z was a non-negative integer. I will also write this using the Vinogradov notation. So as an example, for the simple PQ-adic frame, we then have that this asymptotic means that the following. And now here's the big lemma. Let chi be QQ-adically quasi-integrable with respect to the simple frame, and suppose the restriction of chi takes rational values on n0. Fixing a choice of Fourier transform of chi, let chi n twiddle denote the nth resummation of chi using that Fourier transform. Furthermore, suppose there are positive integer constants, both of which are greater than or equal to 2, such that c is a multiple of q, and that d is co-prime to q, and that chi of z minus the nth resummation has this asymptotic as n approaches infinity. All right, so then, provided that all these conditions hold, for j in 0, 1, we have that the limit as n approaches infinity of our integral converges with respect to the simple 2q-adic frame to this function. Moreover, this thing is 2q-adically rising continuous. So the proof, we start with our formula for LR inverse, which we apply to the nth Dirichlet kernel, and we get this thing. Blah, 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 blah. And then letting j be in 0, 1, and let's call our integral I, R, J, N, I for integral. We have this thing integrated against, since this is a function of z, this thing integrated against chi of y dy, it's just this constant times this integral, which is going to be the 0th Fourier coefficient of chi. And then here, we integrate with respect to chi, and we get this term. This term at the top over here, we don't need to worry about its convergence. Note that this q will converge to 0 q-adically for z and z2 prime as n goes to infinity, and for z in the non-negative integers, this denominator term here goes to infinity in the topology of the reals. So this term converges to 0 in with respect to f2q. So our limit of our integral is this. Now for brevity, I'm going to let a and j denote this. It's the difference between the nth shift of z and j, and then we divide by 2. The integral here can be written like so. This is just comes from just writing out what the big N minus little nth Dirichlet kernel is. Here, we write this as a Fourier series, and then we group the terms, and this, of course, is then going to be the chi hat of 2t. Now, we then write this out like so, and now we're going to use that adjoint identity. We're going to take a 2 from this function and put a 1 over 2 in this function, and we add over even and odd. And when we pull things out, we get all of this, which factors to this. Note that we go from 2 to the big N minus little n to 2 to the big N minus little n minus 1. And so our integral simplifies to this expression, where again, this is the big N minus little n minus 1th partial sum of the Fourier series evaluated at a and j of z, which of course is the same thing as convolution with the Dirichlet kernel, which is the same thing as our twiddle notation. Here, note that if this difference is an odd number, then dividing by 2 will give us a number that's congruent mod 1 to 1/2, and so sticking it on top in the character, we'd get -1, and this would then vanish. So the only way the integral is going to be non-zero is if this difference is even, in which case the sum of this thing will be 2, and so we then have that this is, using our Iverson bracket notation, this is equal to 2 times the Iverson bracket times that. So, in conclusion, what we get from this analysis is that the limit of our integral as n approaches infinity converges with respect to the simple 2q-adic frame to the limit of this thing. And this is what's going to cause us the main source of trouble. Here, we have both the upper limit of summation is going to infinity as n goes to infinity, but we also have an n inside here. When big N is large, this is going to take on very small values when little n is close to big N, and it's going to take on very large values when little n is much smaller than big N. And so in order to, what I want to show here is we're going to first use the standard analysis trick, which is when we have a thing, we will add and subtract something from it. And in particular, we're going to add and subtract chi from this. And when we do that, we're going to end up with IRJN is this thing plus this thing. And here, this we don't need to worry about n, the n's over here. So what we're going to do is we're going to show that this term over here tends to 0 with respect to the simple 2q-adic frame as big N tends to infinity. Now, before we go any further, we need to make an important observation, which is it's quite simple, but it's very important. A and j of z will have infinitely many ones digits, if and only if z has infinitely many ones digits. So, in this expression, we have one of the functions I call 1n and 2n, and I'll be denoting this difference here. This is the partial sum of the Fourier series minus the actual function, and I'll denote this by, do I use the Tweedle notation elsewhere? I think I use the Tweedle notation. Yes, I think I use the Tweedle notation. So I may or may not, sometimes I might write a twiddle over this, whether or not the twiddle is there, the triangle means this difference. So First, we're going to deal with the convergence of 1n. And so our first claim is that as n goes to infinity, this converges with respect to f2q. And of course, since we have two topologies to deal with, we'll deal with them one at a time. Let z be in z2 prime. Then, since chi takes values in zq, we can take the q-adic absolute value, we get this estimate, and this will decay to 0 as n goes to infinity because z is in z2 prime. Thus, this series has terms which tend to 0 q-adically as n goes to infinity, which then tells us that this series converges q-adically for z in z2 prime. All that's left then is for z in the non-negative integers. So fixing such a z, let's pick little n to be bigger than the number of 2-adic digits of z. Then, applying the shift little n times to z gets us 0 because it eats up all the digits. If j equals 1 then, for such n, this is going to reduce to the congruence 0 congruent to 1 mod 2, which is impossible. So if j equals 1, then this bracket is going to evaluate to 0 for all n greater than or equal to lambda 2 of z. So when j is equal to 1, this limit I of in, it converges in the discrete topology to this function. Now, on the other hand, suppose j is equal to 0. Then, when little n is bigger than or equal to the number of the 2-adic digits of z, an 0 is just going to be 0. And so here, picking big N, bigger than the number of 2-adic digits of z, we get that 1n is equal to, here's the sum over the n that are less than or equal to, they're strictly less than the number of 2-adic digits, and then here's where n is greater than. This reduces to 0, 0, which is always 1 when n is in this range, and here this just becomes chi of 0. And remember, we assume that chi takes values in the rationals on the non-negative integers, so this is a rational number, and we get this thing. Letting n go to infinity, this converges in the reals, the geometric series, and so we get the following. So this is the case when j is 0, and this is the case when j is 1. The only difference here is that the j equals 0 case has this extra term here, which we get by taking n to infinity here, so we can combine them into a single case by using an Iverson bracket for j equals 0. So what we want to show is that this thing converges to I infinity, and to do that, well, let's just use our frame to sum I infinity at z in n0, and when we do this, going through the motions, we get the following. And here, if j is 1, this vanishes identically, and if j is 0, this is 1, and this reduces here to 0 on the inside. And so we find that I infinity of z is this, but this is exactly what we found the limit to be. So 1n tends to 1 infinity on n0, and the convergence is in the real topology. Since we've therefore taken care of all the 2-adic integers, this proves the frame theoretic convergence. So all that's left is to show that 2n, this thing, tends to 0. The main observation to get is that we can use our asymptotic estimate on chi to deal with this term. Remember, just recall, our estimate was this, that the difference between chi of z and the nth partial sum of the Fourier series at z is bounded by this frame-wise. So we're going to get a frame-wise bound on this term, and in particular, as the subscript here gets larger, this term is going to get smaller. But unfortunately, this creates a problem. When little n is large relative to big N, this subscript is going to be small, and so this term is not going to contribute decay. On the other hand, if little n is small relative to big N, then this subscript will be large, and we will get decay. On the other hand, so in other words, the decay here is inversely proportional to the size of n, whereas in this expression, the decay will be directly proportional to the size of n. So what we're going to do is we're going to split this sum up into two regimes of n, and then bound this term and that term separately, and then combine everything to get the results that we want. So to start, let's just deal with n0. For this, we're going to use our proposition about counting the number of ones digits in theta, in the shifts. And so in particular, we know that the number of ones in the projection mod 2 to the k of the nth shift of z is given by this thing. Now we make an observation. Since for all this, we're requiring this congruence to hold true, this is the same thing as applying the shift operator to theta n. That is to say, if this number is odd, then this is going to be 1, and then it's the shift operator of that. But if this number is even, then the congruence forces this to be 0, and again, it's the shift operator. So what this says is that when this congruence is true, ANJ of z is theta to the n plus 1 of z. So in particular, we then get, by this formula, here we set, replace n with n plus 1, and replace k with m. We then get that the value of this mod 2 to the m is equal to this difference. So now with our hypothesis, using this on 2, we get the following. So this is just, we're doing the standard triangle inequality bound using the real absolute value. We then use our hypothesis here on the delta term. And so then that's going to become delta, this is c to the number of ones in an and the subscript passes. Here we then use this formula here with little m is equal to big N minus little n minus 1. And now a trick. C and D, this is just to simplify things, C and D are both integers greater than or equal to 2. And as a result, we also note that the number of ones in z mod 2 to the n plus 1 is greater than or equal to the number of ones in z mod 2 to the n. So when we take this, multiply by -1, and stick it on top of c, this turns into an upper bound. And so this should be an inequality. This is a less than or equal to. We just get rid of that n plus 1 and make it an n. And here, these two cancel out with those two. And so now we just group everything. We'll pull out a big N minus 1, and we'll pull out c with the 2 to the big N. On the other hand, c to the little n will go underneath the qr, whereas d to the negative n will go underneath 2 to the r, and so we get this. Now pick n bigger than the number of two-adic digits of z. Then we have, by a constant of proportionality, we pull out the terms where where little n is less than lambda 2 of z or greater than it. This thing is going to be O1, bounded, as big N goes to infinity, and this is a geometric series. So now we just, this right here is going to behave like a O1 with respect to z, and then we have with respect to n, and we have the decay here. So this then becomes O of 1 over d to the n, and then if we write out the whole sum, we get this thing, which when we simplify, this behaves like 1 over d to the n, this behaves like 1 over 2 r to the big N, and this behaves like 1 over d to the n. So we get that, and we get the desired vanishing in the real topology as n approaches infinity. So now comes from the tricky part. We now need to use z and z2 prime, and here, as I said, we're going to need to leverage the fact that this term will be the behavior of these two terms as little n varies with respect to big N. So, in particular, what we're going to do is, so just going through that, if we take the q-adic absolute value, we have that this term right here is bounded by the q-adic absolute value of c to this number. Now we're going to just do some direct counting. So as we see, because since z is in z2 prime, this is in z, a and j of z is in z2 prime, and so it's going to have infinitely many digits. Consequently, as this exponent right there gets bigger, this whole exponent is going to get bigger, and because CQ is less than 1, this is going to decay to 0. So what we're going to do to analyze this is we're going to break this up by using a real number rho between 0 and 1. Like, for example, let's set rho to be 1/2. And then we're going to break up the sum of little n here into two regions. One where little n is strictly less than rho big N, and the other where little n is greater than or equal to rho big N. When n is less than rho big N, we can get the following inequality. And so for a little n in this range, the number of ones here will tend to infinity as big N tends to infinity, and this increase will be uniform with respect to little n in this range. On the other hand, when little n is bigger than rho n, we won't get this decay, but thankfully we don't need to worry about it because the other term will give us the decay as big N goes to infinity. Let's just make everything explicit. In particular, taking n less than the floor of rho big N, this means this is the largest integer less than or equal to rho big N. Just playing around with the inequalities, we get this and this. So since this number is bigger than this number, the number of ones in ANJ mod that is going to be greater than or equal to the number of ones in ANJ mod that. Now we stick this all on top of C's q-adic absolute value, but since that's less than 1, the order of the inequality reverses, and we get that this thing is less than or equal to this thing. Now we're going to do a proposition, number 143, which we'll prove once the rest of this argument is done. And we're going to set gamma, and for that proposition, we set gamma of n to be the floor of rho n. And then for big N, for little n less than rho big N, for z and z2 prime, and assuming that this congruence holds, by proposition 143, this number is proportionally larger than the number of ones in z to the 2 mod floor of big N over 2 minus floor of rho big N. As such, since C's q-adic absolute value is strictly between 0 and 1, we have this term is less than or equal to this guy, and then this guy is less than or is bounded proportionally by this guy. Now a trick. We're going to add and subtract rho from this exponent, and then multiply and divide by n. So here we added and subtracted by rho, and then we multiplied and divided by n. The reason why we're doing this is because this particular ratio is going to be of statistical import relevant to z. If you happen to know about natural densities, I bet you can figure out where I'm heading with this. So, of using this inequality, because again, c is between 0 and 1, in q-adic absolute value, we have that term is proportionally less than this thing. Now, by the root test for series convergence, this sum will converge in R, and necessarily that will force its nth term to decay to 0 in the reals, provided that this supremum holds true. Taking logarithms, we get this. And so now let's replace big N here with 2 big N, and then multiply both sides by 2, we get the following. This right here is the number of ones in z mod 2 to the n divided by n. Note that z mod 2 to the n has n two-adic digits, and so the maximum number of ones this can have is n. So in the limit, this is going to be some number bounded between, it's going to be some number in the unit interval between 0 and 1. By definition, this quantity is what we would call the upper density of the ones in the two-adic digits of z. So, as long as this lim sup is strictly positive, so as long as z has a positive upper density of ones digits, we can then choose rho to be smaller than half of whatever this density is, in which case this lim sup will hold, which means this decay happens, which means this term will go to 0 as big N goes to infinity. And so that gets us what we want. So then for little n less than rho big N, where rho is chosen to make this limit true, we then have this bound, and this term will tend to 0. On the other hand, if little n is bigger than rho big N, we know that this is a q-adic integer, so it's bounded by 1, but we can then use the q-adic smallness of this guy to get this upper bound. And so we then have that the maximum over all little n less than big N of this thing is bounded from above by this guy, which is then this upper bound tends to 0 in the reals as n goes to infinity. This then gives us desired uniform q-adic convergence to 0, and this proves that 2n of z tends q-adically to 0 for all z and z2 prime, provided that all z and z2 prime which have a strictly positive upper density of 1's digits. Unfortunately, if z happens to be a two-adic integer with density 0 number of 1's digits, then this argument falls apart. And unfortunately, there are plenty of such z's. A simple example of them is this following two-adic integer. The fact that this has 1's digits of density 0 comes from the well-known fact that the perfect squares have density 0 in the positive integers. So to modify for this case, we're instead suppose that this limit soup is 0, and then we're going to have to modify our cutoff for splitting up this range of little n's. So here we're going to use proposition 143. Let gamma be an arbitrary non-decreasing function which tends to infinity in the reals as n goes to infinity. And let's suppose that this inequality holds true for all n. Applying proposition 143, which again we haven't proven yet, we get this lower bound, and for some absolute constant depending only on z. Thus, since the CQ is less than 1, we have this upper bound. Once again, we use our trick of multiplying and dividing by n. And once again, by the root test, to get the desired convergence, it suffices to show that this thing the exponent here is less than 0. Replacing big N with 2 times big N, we get this. And by our assumption on the lim soup on the density of z's 1's, this is the same thing as this. And to win, we then pick the following as our cutoff function. It's easy to verify that this gamma then satisfies this identity, and that this tends to infinity as n goes to infinity. When we plug in this gamma of n, note that the 2n and 2n cancel out, and so here this becomes 0, and we get a negative 1/2. So for this choice of gamma n as our cutoff, we get the necessary convergence, which then guarantees that this term tends to 0 as n goes to infinity. So we then have that for n less than the cutoff, the q-adic absolute value of the term is less than this thing, and the upper bound goes to 0 as n goes to infinity. On the other hand, for n bigger than the cutoff, we once again will use this term, and so this thing is bounded above when we let n be everything from 0 to big N minus 1. This is bounded above by this, and this upper bound tends to 0 as big N goes to infinity. So now we've shown that 2n of z goes to 0 q-adically for all z and z2 prime, because every such z either has a positive upper density of 1's digits or has a 0 upper density of 1's digits. So that shows that 2n converges to 0 with respect to our frame. And so putting our two claims together, we have that our limit of our integral was equal to the limit of 2 times 1n of z plus 2 times 2n of z. Applying frame theoretic convergence, we get this, which is just 2 of that, which is just that, which is exactly what we claimed it to be. So this proves that the limit of our integral is indeed frame convergent to this infinite series. So the last thing we need to do to finish up the lemma is to show that this function right here is actually rising continuous. For this, we're just going to do it directly and compute the nth truncation of 1 infinity of z. And just going through the computation, it's actually this the same one that we used when we were dealing with the convergence of 1 infinity over the reals, and we get this. And so we end up having that this expression right here is the nth truncation of 1 infinity. Since this will converge to 1 infinity of z in the discrete topology, whenever z is a non-negative integer, as m goes to infinity, we have that the limit, we have rising continuity in the discrete topology on n0, which means we converge in the q-adic topology there. On the other hand, if z is in z2 prime, this thing tends to 0 q-adically as m goes to infinity, and we then get convergence, and so we win, and therefore I infinity is rising continuous. Next, we give the proof of the so far unproven proposition, the 143 that we've been using in the above lemma. Let n be a positive integer, let gamma be a non-decreasing function satisfying this inequality and tending to infinity. In particular, note that the floor of rho big N satisfies these properties when rho is positive but less than or equal to 1/2. Next, let little n be a non-negative integer strictly less than gamma of big N. Let z be in z2 prime, let j be 0 and 1, and assume that we have our congruence. Then the number of ones in anj of z mod 2 to the big N minus gamma of big N minus 1 is bounded below proportionally by this difference for some absolute constant independent of all the parameters involved. So we have some digit counting. Technically, we could have used that proposition involving how to compute the number of ones digits in theta. That would give us an exact answer, but it turns, for my purposes, just easier to do this approximation. So this thing, note, has this many digits. If we apply the shift little n times, that's going to delete the n lowest digits and then bring in n new digits. The n new digits are going to come from the n minus gamma of big N through this thing, number of digits, none of which were present in our original number. So the number of ones digits that we bring in by applying the shift n times is given by this difference. And so as the lower bound, we have the following. After applying the shift, the worst case scenario is that we lost n ones, little n ones. It means every time we applied theta, we lost a 1. And since we apply theta n times, we are going to then lose n ones from what we had in the original. And then we have to add in the ones that we would potentially gain by having used the shift operator, and that's this thing. Finally, we then are going to apply a shift operator one more time, because going from this quantity to this quantity is going to, at most, take away one additional 1. And now we just use another trick, that this number right here, the number of one digits here, since we reduce, is going to be at most 1 more than the number of ones digits if we are counting 1 less digit. And so this then gives us our bound, voila. And then we just use this inequality on gamma of big N, which we rearrange. And then we have this thing, so we go from there. We get, and n is less than gamma of big N, which flips to that, and then that gives us our inequality. Okay, so then with that proposition, our lemma is fully proven. We're nearly ready. We just have one last thing to do. Here, let f m n twiddle denote the nth partial sum of the Fourier series generated by fm hat. And we're going to suppose that fm is quasi-integrable with this particular Fourier transform. Then we have the following frame theoretic asymptotic. Q to the parity of z over 2 to the power of m times fmn twiddle of the shift function is equal frame-wise to f1 n plus 1 of the shift function of z minus 1 to the m plus the error term. What this is effectively saying is that we can, if we want to understand the nth power, the observation that this is based on is that since f1 is just the original f series, Fm is the original F series to the power of m, so we should be able to express them in terms of one another. Moreover, regardless of whether or not Fm is quasi-integrable, we also have this identity. So as we saw in episode 1, we found the following formula for our nth partial sum of the Fourier series of chi-q. Using our formula relating f1 to chi-q, we then take the partial sums and we get the following. And then by proposition 142, where we which one was that one? That one where we I need to go back and remember. That's not proposition 142. Proposition 142 is that's a lemma. Proposition 142 is, there we go. Yes, it's by this formula for the number of ones digits. By using that formula for the number of ones digits, when we go through the computation, we end up finding that, in particular, we use this to manipulate the number of ones here. So we have various n's coming in and out. We re-index, and blah, 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 blah. We end up with the following identity. That precomposing the shift operator with the nth partial sum of f1's Fourier series is the same thing as doing this. And so if we multiply by q to the z2 over 2, we then get this identity. So what this does is this is showing what precomposing with the shift operator does to the Fourier series of f1. Note that this satisfies this asymptotic frame-wise. We can then rewrite this thing as this asymptotic. So next, since we've assumed that Fm is quasi-integrable, we're going to now use the fact that Fm is just F1 to the power of m. So since we know that this is quasi-integrable, we have Fm is going to be equal to this plus that. And let's see here. Did we need to assume the... I believe we need to assume that Fm... do we need this? Technically, I think that this should be modified. It might not necessarily be this particular asymptotic, but it is a point-wise, frame-wise asymptotic. And so what we get here is that what this is saying is that the nth partial sum of Fm's Fourier series is going to converge frame-wise to Fm. Fm is the same thing as F1. Actually, I don't even need to. No, we don't even need this big O. We can just get rid of it, and then this is going to be in the limit as n approaches infinity. So I would make this little o of 1. This should be a little o of 1. And then we have that F1, of course. This is by we know the convergence formula for F1. We have that particular formula here. And then when we pull everything out, we then get the big O of that guy. And so for fixed z, as n approaches infinity, we multiply this by qz2 over 2 to the m. And then since z and m are fixed, let's see, where did we do with this part? We pull this q inside here. We then use this formula there. And then we use binomial expansion since m is finite. We then get our desired asymptotic. Lastly, for this other identity, Fm of theta 2, if we take the nth root, we get F1 of theta 2, which we can manually compute, and then putting nth powers gives us what we want. Finally, with all this done, we have everything we need to prove quasi-integrability. So the goal here is we're going to apply our lemma inductively, and we're going to use the result that we just proved to show that the asymptotic conditions are satisfied. So our theorem is here as follows. Let f fk hat of t denote the Fourier transforms of these measures as we constructed in lemma 32. Remember, in that lemma, what we did is we started with f0 equals 1, and then f1, we knew its Fourier analysis, its Fourier transform from episode 4, and then we used that with our LR inverse operator to then construct the measures fk of z dz for all k greater than or equal to 1, and these guys were then distributional solutions of the fk's functional equations. What we're now going to show is that their Fourier transforms actually generate Fourier series that converge frame-wise to fk, and we're going to proceed by strong induction on k, which means that we're going to be not only assuming the kth case, but that every case up to the kth case. So for our base case, we just did this. It's what we did with chi-q. We use chi-q, and then to get a formula for f1 hat, and f1 hat, then because this converges to chi-q of z, when we sum the Fourier series, this converges to f1 of z, and we're done. So now for the strong inductive step. Fix r greater than or equal to 2, and let's suppose that we've shown that f little k is quasi-integrable for all k less than our r, and that it has a Fourier transform fk hat. Using these Fourier transforms to get measures, and then in particular, we have that these measures, if we let d mu denote the measure that we can then define fr of dy, and we're going to call this measure d mu. So we've assumed that the fk's are quasi-integrable, and that we have measures from them, and with this, we'll then construct a new measure, which we're going to call fr of dy, and then we're going to show that this particular measure's Fourier transform actually generates a Fourier series which converges to fr. So in particular, by our previous work, this is what d mu does to a given g, and we know that mu hat has to satisfy these functional equations. So to conclude, all we need to do now is that show that when we pick g equals the Dirichlet kernel, then as n approaches infinity, the right-hand side will converge with respect to the frame to fr. We do this in two steps. First, we show that the fk's must satisfy the hypotheses of our big lemma, and then we apply the big lemma. And then once we're done with that, we'll use the functional equations to show that the limit that we've computed here is in fact equal to fr. So let's deal with the hypothesis satisfaction. So fix a positive integer m, and suppose that fk is quasi-integrable using our construction with the LR inverse, and that its Fourier transform is fk hat for all k, and then of course f1 hat is given by this. Then for every such k, the difference between fk of z and the nth partial sum of fk's Fourier series satisfies our lemma 33 requirement. So we're going to do again by strong induction. So we start with the k equals 0th case, but this works because f0 is just 1. Next, letting k equals 1, as we saw in the proof of our previous proposition, f1 and twiddle we computed explicitly. And since we know that f1 is equal to this case either that series or that series, when we subtract everything, we get this as the explicit error estimate. So when z is in z2 prime, we take q-adic absolute values, and we have that bound. Whereas when z is in n0, we take real absolute values, and we get that bound. So our lemma 33 condition holds for k equals 1 and k equals 0. Now, using our functional equation, we'll sum the Fourier series, and we get this relation. We then apply our adjoint identity to get this equation. So here, again, we just break it up into the t over 2 and t plus 1 over 2. And then when we rewrite this, we get the following. And then we observe that this is going to be the indicator function for z times z congruent to 0 mod 2, and this is the indicator function for z congruent to 1 mod 2. And so then we can again combine this using the shift operator, like so. So we have that this formula, when we sum the Fourier, when we sum the right-hand side, we end up with this identity. Similarly, here are the functional equations for the full F series, And we can rewrite these using theta 2, like so. And so now we will subtract this equation from that equation. And we get this thing. So remember, we assumed that fk was quasi-integrable for all k in 0 up to big M. So because we have quasi-integrability, we then use our proposition with the big O estimate to say that this function right here, we can express it like this. Additionally, by that same proposition, we have that this function is equal to this. So this difference is going to become now a difference of these kth powers. When k is greater than or equal to 1, then we factor things out. And so here it's f1 of z minus f twiddle of 1n plus 1 times this stuff. But this stuff doesn't matter because it's going to be bounded frame-wise, point-wise in z. So actually, when we take the limit as n approaches infinity, we get that this is going to be converging to this quantity. So this part is so what we get is this part's going to be bounded. Here it's O1, and so in particular, we see that this thing is just going to be O1 with respect to our frame times this difference, and so this shows that the decay condition on this difference then can be passed to the decay condition on this difference. So putting everything together, this difference is then equal to this thing, which as we saw is a big O, and since M is finite, we get everything we want. So this proves the desired estimate, which as we saw was this one, that for every such K, this estimate holds. So with that being done, now we apply lemma 33, where we set G to be the Dirichlet kernel, and then we take our limit. These are the two integrals that we computed using our lemma. So now we just use the lemma, and this is the correct formulas for them. And we can combine these into one by summing from j equals 0 to 1. So we have this thing. Now let's denote this messy guy by big F of z. Lemma 33 then tells us that big F of z is 2q adically rising continuous. And if just by our standard episode 1 type computation, we then see that f of 2z plus j satisfies this functional equation, but then that, which by our unique functional equation characterization of fr, this forces big F to be equal to little fr. So what this then shows is that the resummation of the Fourier series generated by the Fourier-Stieltjes transform of this measure, which we have constructed recursively, is then going to converge to the F series of FR, and we're done. So that shows that FR is indeed quasi-integrable, and we then get the quasi-integrability of chi q to the R by just rewriting it using our this identity. And so since all the FKs are quasi-integrable, so are the chi q's of R's. Now, because I don't want to keep delaying the presentation of this video, I'll leave the following as a conjecture for now. Consider functions fg of a p-adic integer variable taking values in, like, let's say the same they take values wherever it makes sense, and satisfying these functional equations. Then I conjecture that if both f and g are quasi-integrable, then so is their pointwise product, f times g. Obviously, a massive improvement of this conjecture would be to show that f to the r is then quasi-integrable for all r. Finally, as promised back in the previous video, here's the formula for our nth-fold product. And here we have these n's, little n's are arranged in increasing order. And again, I forgot the 1 over 2 to the n. Yeah, this should be divided by 2 to the little n big L. And so for this one, there should be a 1 over 2 to the little n subscript 4. And so you can see how things are going to get exponentially more complicated as we increase the number of the value of r. And the proof is just do it. Computation. Blah. 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 And I have to divide. And then I think I forgot that fact. Yeah, there's the 1 over 2 to the NL that I forgot to take into account. So, now let's go back to where we were at the beginning of the previous video. Formally, as we saw, we have the following Fourier transform pair, that the reciprocal of chi-q of z minus x should have this as its Fourier transform. And so, in theory, one way to try to use all of this, by way of the Tauberian spectral theorem, would be to attempt to unlock the secrets of this convolution as n approaches infinity, and then use them to study this partial sum as n goes to infinity. And in theory, if you were looking at this, you would then be able to get up an explicit system of congruences in terms of x, whose solutions would then be, let's see, provided you would then repeat the stuff that we did in part 1 of episode 8, and we would then get an alternative way to do the spectral theoretic stuff. Now, to that end, it's also conceivable that we might need to exploit the properties of degenerate measures. Namely, that if we get chi-q hat, we can then change chi-q hat by any degenerate measure mu hat, and then we would still get a Fourier transform. And so we could, if we can show any x's that we can prove or disprove as a periodic point with any particular choice of mu hat, any of them will work. So that means that it may be the case that we need to exploit the properties of those degenerate measures in order to get the most bang from our buck out of our Tauberian spectral analysis. So now we get to the final part. So